So now we know what standard form is. We're also going to talk about factored form today and how to convert between factored form and standard form. We're also going to talk about what a relative minimum and a maximum would be in a function and how to find it. All of that is going to be in this video. Let's go ahead and get started. So let's start by taking a look at this equation. This is factored form because these are as factors as we can get to this equation. And so what we want to do is write this in standard form. And so this is very similar to some of the questions you had on your homework assignment last night. In order to put this in standard form, we're going to have to multiply these two things together. But before I can take 3x minus 7 times x plus 5, I'm going to have to square the x plus 5. So the 3x plus 7 is not going to change, but the x plus 5 can be written as x squared. I'm going to have plus 10x and then plus 25. And what I really did there is I just took the x plus 5 and multiplied it by itself. So if I took x plus 5 times x plus 5, and I did it the long way here, x times x would give me x squared. Then I would have a 5x and another 5x, which gives me the 10x, and 5 times 5 is 25. Well, then I'm going to have to multiply these two factors together. So I'm going to take 3x times x squared, which is 3x squared. 3x times 10x is 30x squared. This should be x to the third here. And then 3x times 25 is 75x. So I've multiplied the 3x out. Now I'm going to multiply the negative 7 out. Negative 7 times x squared is negative 7x squared. Negative 7 times 10x is negative 70x. And then negative 7 times 25 is negative 175. So if I simplify like terms, I have my lone x to the third term, which is 3x to the third. But then I have 30x squared minus 7x squared, which is 23x squared. Then I have a 75x minus a 70x, which is plus a 5x minus the 175. So this is a cubic equation because the highest degree here is a third degree polynomial. It's a polynomial with 4 terms. The leading term here is the 3x to the third. The leading coefficient is 3. My constant term is negative 175. I have a quadratic term here, and the coefficient of the quadratic term is 23, and the coefficient of the linear term here is the 5. And so there's our answer, 3x to the third plus 23x squared plus 5x minus 175. What I'd like to do right now is to consider what the graph of this would look like. So you can take out your graphing calculators and try to graph this right now. You're going to get something that's a little unusual, a little different than a lot of the graphs that we've had before. But I'm going to have you go ahead and pause the video and graph this equation on your graphing calculators and just see what it looks like that you get. So hopefully you've done that. Now if you really scrunch the y-axis down, you're going to get something that looks kind of like the graph that I've drawn here. And I have this question here that I want you just to start thinking about. It's not really in our lesson for today, but as you approach the lessons that we're going to get in the future, it looks like it hit right here. There's a 0 right there. There's another 0 right here. It looks like this 0 is at 5, and this 0 is a little bit more than 2. Is there a way that we can look at this equation specifically in factored form and know that the zeros are going to be at a little bit less than negative 2 and then at positive 5? And there is. I'm not going to tell you what that is yet. I want you to think about it before I tell you what it is. Let's go on to a different question. So here we have an equation that is right now in standard form, and what we want to do is put it in factored form. So what I'm going to do is factor first a 2x out because 2x goes in all 3 of these terms. Right now this is a cubic trinomial, and so I'm going to factor a 2x out, which means I'm going to have an x squared here plus an x here minus 20 here. And so the reason I got those values because 2x squared times x, or 2x times x squared is 2x to the third, 2x times x is 2x squared, and 2x times negative 20 is negative 40x. But I can factor this further. The 2x is going to stay on the outside, but then I can factor the x squared plus x minus 20 to x times x, because that multiplies together to give me x squared. And then if I want a positive 5 and a negative 4, 5 times negative 4 is negative 20. And if I check my inside terms and my outside terms, that's 5x minus 4x, which does give me x. So in factored form, it's going to be 2x times x plus 5 times x minus 4. So that's what it looks like in factored form. But I want you to think about what the graph of that would look like if it's y equals 2x times x minus 4 times x plus 5. And I just want to talk you through this a little bit on this problem. We're going to have 3 zeros here. It's going to hit the x-axis 3 different places. Can we figure out where those 3 places are? In other words, there's going to be 3 values of x that are going to give me a y value of 0. On the graph, here's where y is 1, and here's where it's 2, and here's where it's 3, and here's where it's negative 1. But when it's 0, I'm going to be right on the x-axis. And so if I were to solve this equation, just like we did in our quadratics unit, if I'm multiplying 3 things together that gives me 0, one of those things has to be 0. Either the 2x is going to give me a 0, or the x minus 4 has to be 0, or the x plus 5 has to be 0. So I have 3 equations here. If I solve the first equation, get the x by itself and divide by 2, I'll have x is 0. That's one term, that's one number that if I stick it in here, it's going to give me a y value of 0. If I solve this second equation, if I add 4 to both sides, x is going to equal 4. If I plug 4 into this form or this form, it's going to give me a y value of 0. And if I solve the last equation, if I subtract 5 from both sides, it's going to be x equals negative 5. And so there's another, whether I plug it into the factored form version of it or the standard form version of it, it's going to give me a value of 0 back out. So in other words, when x is 0, y is 0. When x is 1, 2, 3, 4, y is 0. When x is negative 1, 2, 3, 4, 5, y is 0. So it's going to hit the x-axis in those 3 places. And you can tell when you graph this that the actual graph is going to do something like this. Now, I'm not going to go into how high it's going to go here or how low it's going to go here. The only thing I'm going to say here is that these are called a relative maximum here and a relative minimum here. It's relative because it's really not the minimum. The minimum is here. It goes down forever. But this is a relative minimum if we're just looking at a certain domain value that maybe goes from 0 to infinity. This is a relative maximum. It's not the actual maximum because this goes up forever. But it's a relative maximum if my domain values are less than 0. And so we're going to look at to see how we can use the relative minimum and maximum to answer some questions. Let's take a look at this example here. Suppose you have some carry-on luggage and you want to make your luggage the biggest volume possible that is legal on a certain airlines. So let's say that a certain airlines has 2 standards. First, the length in any carry-on luggage is to be 10 inches longer than the width. And then it also has a stipulation that the sum of the length, the width, and the height has to be less than 40 inches. So with those stipulations, we want to make the biggest bag with the biggest volume. Well, that means we're going to have to write an equation for the volume. We know that the volume is equal to the length times the width times the height. But we don't want 3 variables. We just want 1 variable. So what I'm going to do is come up with what our variables are going to be. We know that the width is okay, so I'm going to let 1 variable be w. The other variable is the length. Well, because of the first expression, the length is 10 inches longer than the width. That means the length can be written as w plus 10. But then we also need an expression for the height. And so the second expression says that the height plus the width plus the length, if I add all 3 of those together, that has to be less than 40. I'm going to push the envelope and we're going to say it's equal to 40 because we want to make the biggest bag possible. And so what I want to do then is solve this for h. I can do that if I subtract w from both sides and L from both sides. But I don't want to use this as my expression because it has both a W and an L in it. So what I'm going to do is replace the L with what L is equal to over here, which is W plus 10. So it's going to be 40 minus W, and then minus W plus 10. I'm going to simplify this. It's going to be 40 minus W, and then minus another W, and minus 10. Well, if I put all those together, I have a minus W and a minus W, which is a negative 2W, and 40 minus 10 is 30. So that means my expression for H could be negative 2W plus 3. So that means if I go back to my volume, my expression for my volume, or my equation for my volume, it's going to be the length times the width times the height. Now the width is W. The length is going to be W plus 10. And the height is going to be negative 2W plus 30. Or plus 3, not 30, plus 3. So this is what it looks, oh no, that is 30, plus 30. So this is what it looks like in factored form. Now I could put this in standard form. I'd have to distribute my W here. So it's going to look something like this. It's going to be W squared plus 10W. But then I'd have to multiply that times negative 2W plus 30. So if I do this, I'm going to have a volume that is going to be W squared times negative 2W is negative 2W to the third. W squared times 30 is plus 30W squared. 10W times negative 2W is negative 20W squared. And then 10W times 30 is plus 300W. And if I simplify that, I'm going to get this expression, negative 2W to the third plus 10W squared plus 300W. And that's what this expression looks like in standard form. Well, now I'm going to get my calculator out so that we can look and see what the graph of this looks like. So I have my calculator out now, and I typed the equation in both forms, really. Here's what it looks like in factored form. I used x's instead of w's. So instead of W times W plus 10 times negative 2W plus 30, I have X times X plus 10 times negative 2X plus 30. Or you can type it in standard form. And that's what I have here, same as this one here. And if I graph both of those, they're going to look like it's just one graph, but that's because one is on top of the other. And so I also changed my window. If you press graph right now, you're probably not going to get that graph because I had to change my window where my X values go from negative 15 to 20, and I'm counting by twos, and my Y values go from negative 2,000 to 3,000, I'm counting by 500s. But the reason I wanted to show you this is because the question was, what is the maximum volume? Well, we're only interested in the domain values that are positive. Remember that our X value represents the width. It would be impossible to have a width of negative 2 or negative 4 or negative whatever it is. So none of this is going to really help. I can't have a negative volume, so this is kind of not applicable to our situation. But over here it is. If I have a width of 2, my volume is going to be up there. If I have a width of 4, my volume is going to be higher. Or a width of 6, my volume is going to be higher. The question is, what is the maximum volume? Well, that's this point right up here. And how do I find that point? Well, on your calculators, you can go to second, calculate, and I want to find a maximum point. So I'm going to go down to number 4 and hit enter. And now I have this little cursor on the line. You can see right here it says, give me a left bound. So the calculator wants to know how far to the left should it go. Well, I'm just going to make sure I'm to the left of my maximum point, my relative maximum point. And you can see this arrow. I'm going to move over. This arrow stays the same. That means I'm going to be somewhere between this input value and some right bound. Well, I'm going to move to the right of that maximum point. So I think that's far enough. There's my right bound. I'm going to click enter. So it's somewhere between these arrows. I'm telling the calculator I want to find the maximum value of that function that's there. It's saying, do you want to guess? And I don't. I just want it to tell me. The maximum point between those two intervals that I put on the calculator is that I want to have a width of 8.93, and my maximum volume is going to be 2,052.2052 cubic inches. And so that's the answer to our question. What is the maximum width that we could have is 8.93, and the maximum volume is going to be 2,052 cubic inches.